Okay, so welcome to this first ever video run through of a practice RPA exam, one of the great moments in history. We can do this fairly quickly, one question per film. Obviously what you can do is make use of your pause button so that you can stop to savour the moment when there's something you particularly want to think about. Okay, so let's make a start. You should be looking at this kind of stuff if you're looking at the right paper for the first question. And the first thing it asks you to do is to name this compound. So you can hopefully recognise that it's a kind of phenyl diazonium ion, and specifically those two methyl groups mean it's 3,5-dimethyl phenyl diazonium chloride. Don't forget the chloride. When it asks you to name a compound, you mustn't just name part of it, not just the individual ion. So 3,5-dimethyl phenyl diazonium chloride. Okay, then it asks you how to make it, starting from this compound, 3,5-dimethyl phenylamine. So what you need is, first of all, nitrous acid, HNO2. Okay, not nitric acid, not HNO3, which you use for nitration. This is nitrous acid, HNO2. And you also need aqueous hydrochloric acid. Okay, so those are the two reactants. To balance up that equation, you're going to need 2 waters on that side. So that's your equation. The conditions are that you've got to keep it below 10 degrees C. That's important because this is not very stable. It will tend to decompose if you let the temperature go much above that. The other thing that's worth mentioning in passing is that nitrous acid is not a stable acid. You can't keep it in a bottle. So what you sometimes need to be aware of is that you can make that in the pot from sodium nitrite, NaNO2, plus HCl. So sometimes when you see the recipe, it says sodium nitrite plus HCl because that generates the HNO2 in the pot. Okay, having made the phenyl diazonium ion, what you do with it is turn it into an azo dye, and that's what this compound is, which is what it asks you about next. And specifically it asks you to identify the functional group, which is that, and that's simply called an azo group. So that's quite straightforward. Then we get to the mechanism. Now this is less straightforward, this is not on the syllabus. On the syllabus it just says this is a coupling reaction and you need to know what the conditions are and you need to know what the outcome is. But in reality, it is an electrophilic substitution. So you could be asked to think about what the mechanism might be by analogy with the electrophilic substitutions you know about. So if you couldn't do this bit, what you need to do now is go away and look at the mechanism of nitration, look at the mechanism of reaction of benzene with halogens, and see that this is very similar. So revise those first and then have another go at this. Okay, so here we go. This is the electrophile, the phenyl diazonium ion. Remember, the positive charge is the key because that makes it attractive to the pi electrons in this ring. And the key step then is that a pair of those pi electrons leaps out and attacks that nitrogen. Okay, so it's curly arrow means 2 pi electrons, a pair of pi electrons moving out from there and being grabbed by that nitrogen. At the same time, one of the components of this triple bond breaks. Now you know that has to happen because what you end up with has only got a double bond there. So you know that bond's got to break, and it breaks now because this pair of electrons is basically pushed out by this pair. So you need a second curly arrow like that, and that gives you your intermediate Y, which you're then asked to draw. So let's do that. Here's the first ring. This one wasn't involved in the reaction, so it just sits there quite unchanged. Then we have our new azo group that we've created, and then we come to the other ring, and this is the one that was involved in the reaction. Okay, so the important thing is that in here now we don't have 6 pi electrons anymore, we just got 4 because 2 of them have gone out to form that bond there. So now we have this kind of intermediate. Okay, 4 pi electrons spread over 5 carbons. So we're an electron short, that has a positive charge. Okay, so remember you've got to be able to draw that sort of intermediate, and the hydrogen that was at that carbon is still there, it hasn't broken away yet, so you draw that on as well. Okay, so that's what you should have for Y. and you can then show how the proton breaks away. So this bond breaks and the 2 electrons go back into the ring like that, and that takes you down to here, and you're left with H plus released from there. So the final step is that you've got O minus here, which is quite basic, and the phenols are only weak acids, so this O minus is good at picking up H plus, and so it will simply grab that one using its lone pair like so, and that takes you through to the final product. Okay, the final thing it asks you to do is to explain how come this works, but if we just used benzene as an electrophile, benzene to react with the electrophile, then it doesn't work. So this is just a variant on the question that they often ask, which is why is phenol, or in this case phenoxide, more reactive than benzene? So let's go through that, because it's an argument you need to have well rehearsed. The argument is that this oxygen has got a lone pair of electrons which can become delocalized into the pi electron system of the ring. Remember, it sits in a p orbital which lines up with the rings of electrons in the delocalized system. But all you have to say is a lone pair on the oxygen becomes delocalized into the pi electron system of the ring. The effect of that is to increase the electron density in the ring, and that makes it more attractive to electrophiles. Okay, so lone pair of electrons delocalized into the pi system of the ring, increased electron density in the ring makes it more attractive to electrophiles. Okay, that's it for question 1. We're going to stop there. I'll see you again shortly for question 2.